All right, we'll pick up the lecture where we left it off last time. We had been talking about ion transport in polymers, and particularly in charged polymers, to contrast it to our earlier discussion about ion transport in uncharged polymers. And we had started with a description of processes where ion transport in charged polymers are important, and in addition to things like controlled drug delivery of charged drugs like proteins and other molecules, it's very important in applications such as reverse osmosis for desalination and also electrodialysis, and we gave examples of those. And then we started to talk about the fundamentals of ion transport in polymers and noted that the overarching model of the solution diffusion model, where ions dissolve into non-porous polymers and then diffuse through them, applies equally well to gas transport as it does to water transport, and now also ion transport in polymers. And we, because the ions have charge to them, we have more than one possible mechanism of transport. That is, more than transport just driven by concentration gradients. We can also have transport driven by electric field differences. And so we use the Nernst-Planck equation, which is an extension of Fick's law, to the case where both concentration gradients and electric field gradients can contribute to ion transport. And then we were working through the basics of that to show how both salt permeability, that is concentration-driven ion transport, and ionic conductivity, or field-driven ion transport, both depend on the concentrations of ions, both cations and anions, in the membrane, and the mobility or diffusion coefficient of cations and anions in the membrane. And this is fully in accordance with expectations from the solution diffusion model, that in order for ions to transport across a non-porous polymer membrane, they have to dissolve into the membrane and then diffuse across it. And in the first part of this lecture, we talked about the so-called Dannon model for ion sorption into charged polymers. We showed how that model typically fails, and we identified what we believe is the basis for that failure, and that is the fact that historically people have not properly accounted for activity coefficients, thermodynamic activity coefficients of the ions in the membrane, and in some cases even in solution. And so now we had a model, the so-called Manning model, used to calculate ion activity coefficients in the membrane, and we got much better agreement with the ion sorption isotherms and the model predictions. Now we're going to go on to a calculation of ion diffusion coefficients and modeling of that phenomena. And before we do that, I'll just briefly recap how the trends in salt permeability and ionic conductivity as a segue. So first, a note here about how one measures salt permeability. In the laboratory, at least, a common way or an easy way to do this is to take a membrane, a non-porous membrane, and to sandwich it between two aqueous solutions, one called a donor solution, so the subscript D represents donor, and one called a receiver solution with a subscript R. In this particular case, the donor and receiver solutions have the same volume of solution V. That doesn't have to be the case, but it's convenient from an experimental point of view. And there is a probe of some sort. Typically we use just an electrical conductivity probe in the receiver solution to measure the concentration of ions in this solution. At the beginning of this experiment, with a membrane sandwiched between these two solutions, a salt of interest is added to the donor solution, and so the donor concentration of salt becomes a fixed value, say 0.1 molar or something of that nature. The receiver solution concentration starts out essentially at 0, so just deionized water in this chamber. The magnetic stir bars keep these solutions well stirred so that the rate limiting resistance to mass transfer is the ion transport through the membrane. And so with the concentration gradient from left to right in this device, there will be a natural gradient for salt to diffuse from the donor cell into the receiver cell. Now, we should also note that there is a corresponding flow, an osmotic flow of water from the receiver cell to the donor cell, but that really doesn't materially impact the analysis that we're going to talk about here, so I won't pursue that further at this point. One can perform a pseudo-steady state analysis, a mass balance essentially, on this system and derive the expression that's shown in the boxed, red boxed expression here. And it gives a relationship between the receiver cell concentration at time t, the donor cell concentration at the beginning of the experiment, the volume of solution in either cell, the area, cross-sectional area of the membrane, and the membrane thickness, and sets that equal to the permeability times time. Now I will note here that in the next slide we're going to write this permeability with brackets around it as an average permeability, and in fact this permeability should have brackets around it as well. It is a so-called average permeability from this experiment, so please make that correction in your notes. And so what this expression tells us is that by monitoring the receiver cell concentration with time, that's the only variable that is changing on the left-hand side of this equation. By monitoring the receiver cell concentration versus time and plotting the data in this fashion, the slope of the resulting straight line versus time gives us the salt permeability coefficient through that membrane. And remember, the salt permeability coefficient is the flux of salt through the membrane times the thickness divided by the net driving force, which is approximately CD minus CR at the beginning of the experiment. You'll also note that in this expression, like in many transport phenomena expressions, you can see things like surface area to volume ratio coming into play, and that shows up in many examples throughout transport phenomena. Now, this is an example of salt permeability coefficients, and now I've put the brackets around the salt permeability, which I should have done in the previous slide. For a couple of the ion exchange membranes and cation exchange membrane with sulfonate groups and an anion exchange membrane with quaternary ammonium groups. And you can see that the permeability increases by several orders of magnitude as that upstream or donor sodium chloride concentration increases. And you can imagine that if you were doing a desalination operation, you would want, by reverse osmosis at least, concentration-driven transport, you would want to minimize the salt permeability and maximize the water permeability. And so if the salt permeability were changing dramatically with salt concentration, this could mean that your ability to purify the water was also changing significantly. And in fact, that's what you see with these types of membranes. And the membranes that are actually used in that application have less charge on them, and as a result of that, these curves of permeability versus upstream salt concentration are much flatter. It's much less sensitive to salt concentration. I'll go ahead and say now that the reason for this dramatic increase in salt permeability is really related to the Danon exclusion. If you remember back a few slides, and I'll just step back here just a bit, in every case where we modeled the co-ion transport in membranes versus external salt concentration, we saw rapid increases in co-ion transport in absolutely all cases. I'll just remind you of that again. And counter-ion concentration changed little, within about 10–15% in this case, over those ranges of salt concentration. And so the reason for this large increase in salt permeability through these membranes is really the breakdown in Danon partitioning, or the Danon exclusion. And as you go to higher and higher salt concentration, there are more and more co-ions in these membranes. Remember, they have plenty of counter-ions balancing the fixed charges, and if there are more and more co-ions in there, then the salt transport can occur faster, because you simply have higher solubility of the mobile salt, which is the co-ions plus their counter-ions. Now we'll go into a slightly deeper analysis of this. As I said, this average permeability comes about in an experiment where we start the salt concentration at a given value, and we initially permeate into a downstream chamber where the salt concentration is 0. Now, often we run these experiments under cases where this concentration never gets far above 0, and so for all intents and purposes, the driving force for transport is just the upstream salt concentration minus 0, and then that average permeability over the course of this experiment is the pseudo-steady state flux of salt times the membrane thickness divided by that concentration. I've switched nomenclature here a little bit because this is going to be the nomenclature now that ties us back to the nomenclature we were using earlier in the ion sorption studies, where CSS is the concentration of salt in the solution, in this case in the donor cell of that experiment. Now, the fact that permeability changes by almost 2 orders of magnitude as the upstream salt concentration changes gives us an additional mathematical issue that we have to deal with. That is, when we have a high salt concentration in the donor cell and a low salt concentration in the receiver cell, then the salt permeability or the transport coefficient that the salt will experience as it goes from high concentration side of this membrane to a low concentration side will vary similarly by perhaps more than an order of magnitude. And this average salt permeability that we measure reflects the permeability coefficients that the salt sees as it goes across that entire membrane. It turns out that to compare with the ionic conductivity measurements, where the salt concentration is going to be the same on both sides of the membranes, but we're going to apply an electric field, it turns out that we need to know the salt permeability at a particular or precise concentration of salt and not just the average salt permeability. Now, the tools to convert these average permeabilities to so-called local permeability coefficients, or permeability coefficients that would be accurate at a specific concentration, is well known in the literature. You can work through the mathematics, and this average permeability in this particular experiment is just the integral average of the local permeability coefficient over the entire range of salt concentrations experienced in that membrane, going all the way from the downstream side at 0 to the upstream side at the concentration of salt in the external solution. We can use standard rules of calculus to bring this salt concentration in solution over to the left-hand side, and then take the derivative of it with respect to the salt concentration in solution, and this gives us directly the local salt permeability coefficient. So we take our average salt permeability data that we get out of this experiment, multiply it by the upstream salt concentration, plot that versus salt concentration, and take the slope of the resulting line, and that will give us the salt permeability coefficient at any local salt concentration, and we'll call this the local salt permeability coefficient. Now, we can write the Nernst-Planck expression for the flux of an ion through such a membrane. I've shown you this earlier. The variables have the same meaning as before, and I've also put in an additional term that would account for the possibility of convective flow of salt through the membrane. And this convective flow can occur essentially, well, a dominant contribution is actually the backflow of water, the osmotic flow of water from the pure water chamber into the saltwater chamber. And it turns out that a more complete analysis of this shows that this effect can essentially be ignored, and as a result, one can write the flux of ion I, like sodium, as shown here, and write an equivalent expression for ion J, which would be chloride if we're analyzing sodium chloride permeability. We can enforce the fact that there is electrical neutrality in this solution, and that will lead us to an expression for the local salt permeability coefficient that's shown here. And this expression again includes the both the cation and anion diffusion coefficients in the membrane, as well as the concentrations of cations and anions in the membrane. And this grouping of terms we often write as the salt diffusion coefficient. And remember, we can do that in the concentration-driven experiment because for every sodium to cross from one side of this membrane to another, it has to have a chloride with it. And so there is an average or effective diffusion coefficient that governs the migration of sodium chloride through that membrane. Now, one of these ions often will be faster than the other, both in water and in the membrane. And what happens is if you have an ion that diffuses faster than another, say the cation is diffusing faster than the anion, then the cation will get a little ahead of the anion, and that charge separation will set up an electric field that acts to retard the cation transport and accelerate the anion transport. And so overall, at steady state, the ions are drifting through the membrane at an effectively a constant diffusion coefficient. The second term is the change in the concentration of mobile salt, that would be coions, in the membrane relative to the change in the concentration of salt in the external solution. So this is just going to be the partition coefficient or the sorption isotherm. So again, this reduces essentially to P is equal to the diffusion coefficient of salt times the solubility of salt in the membrane. And again, these ions go together through the membrane because they are electrostatically coupled. You can't have just cation transport or only anion transport through these membranes, such membranes at steady state under only a concentration gradient driving force. And so this shows the diffusion coefficients of salt in the membranes that we've been discussing. And that diffusion coefficient comes directly out of the permeability expression, where we have measured the salt concentration in the membrane and the external solution. We've measured the permeability, and then use those two values to calculate salt diffusion coefficients. And you can see that they exhibit much less concentration dependence than the permeability coefficients. And so that again affirms that the steep increase in permeability that we observe in this experiment, the steep increase in permeability with concentration, is coming about because of a substantial change in the concentration of mobile ions with external salt concentration. Now, it turns out that in a cation exchange membrane, as we've seen before, the concentration of cations in the membrane is enormously larger than the concentration of anions in the membrane. If we go back a few slides, let me take you back to this slide. In a cation exchange membrane, the concentration of cations in that membrane is enormously larger than the concentration of anions. And that has a real consequence for these diffusion coefficients. So in the cation exchange membrane, the concentration of cations, say sodium ions, is much greater than the concentration of chloride ions. And if you just plug that into this expression, setting C plus in the membrane much greater than C minus, what it turns out is that the salt diffusion coefficient is about equal to the anion diffusion coefficient, or the chloride diffusion coefficient in this case. So what this is telling us is that in salt permeability through charged membranes, it's the diffusion coefficient of the rare species, the diffusion coefficient of the excluded species, that is the gatekeeping or rate limiting step in determining the diffusion coefficient of salt through the membrane. And you can imagine that if there are very few chloride ions in that membrane and a lot of sodium ions, orders of magnitude more sodium ions, but that the membrane has to remain electrically neutral, the only way that a sodium gets out is if a chloride goes with it. And so the sodium chloride transport is limited by the chloride transport. The rare species dominates concentration gradient driven permeation in such materials. In an anion exchange membrane, where we have positively charged, for example, quaternary ammonium groups on those polymers, and therefore a high concentration of anions of chloride, for example, and a low concentration of positive ions like sodiums, then the situation is reversed, and the salt diffusion coefficient is dominated by, again, the diffusion coefficient of the rare species, which is the cations in that particular case. Now, we'll turn over a bit to discuss ionic conductivity, and in this case, we have a scenario where we have a very similar device with salt water on both sides of a membrane that's sandwiched in between. And here the salt concentration on either side of the membrane is exactly the same. And we apply an electric field with these two electrodes to drive cations in one direction and anions in the other. And the electric current, by definition, can be written as the Faraday constant. That's the number of coulombs of charge that can be transmitted by a mole of ions. And then here is the net flux of here's the flux of ions through the membrane, and that basically is telling us how many charges have to be moved to keep the sodium going in one direction and the chloride going in the other. And together that gives the current. Starting from the Nernst-Planck equation, in this particular experiment, we have no concentration gradient, so the first term goes out, and we can write the ion flux for both the cations and anions for all ions in the salt solution, and we just plug that into this expression for the current, and we can derive the expression that is shown here for current in terms of the electric field gradient, square of the valence, concentration of each ion in the membrane, and its diffusion coefficient. The definition of the ionic conductivity, which is what one generally measures in this experiment, is the ion current. So this is the number of ions that can be moved per unit membrane area per unit time. That'll be the ion current. And that normalized by the driving force, which is the electric potential difference per unit thickness of membrane, is the definition of the ionic conductivity. And so if we use that definition in the expression that's shown here and apply it to a one-to-one electrolyte so that these valences are plus 1 for sodium and minus 1 for chloride, they're squared, so they both just end up being 1. And the ionic conductivity then depends on the square of the Faraday constant over RT times the concentration of cations in the membrane times their diffusion coefficient, and a similar expression for the anions. Now, remember, for permeability, for concentration-driven permeability, it was the concentration and diffusion coefficient of the rare species, that is the coion, that dictated the permeability coefficient. The situation here is opposite with conductivity. It is the majority species that carries the vast majority of the current. And so in a cation exchange membrane, so that, for example, a membrane with sodiums or with sulfonates on the backbone, the concentration of sodium, if we have a sodium chloride electrolyte, concentration of sodium in that membrane is orders of magnitude, under most cases, orders of magnitude more than the concentration of chloride. The diffusion coefficients are within a factor of 2 or so of one another the same, and so you can imagine that in a cation exchange membrane at low salt concentration, this term is going to dominate. That is, most of the charge or current is carried by the dominant species in the membrane. So that's the opposite from the permeability expression. And so this is our final expression for ionic conductivity. And in the cation exchange membrane, where we have a great deal more cations relative to anions, you can see that this expression then would simplify when C plus M is much greater than C minus M. We get the expression shown at the bottom of the page. That is, most of the charge is carried by the cations. In the anion exchange membranes, that is the ones with the quaternary ammonium fixed charge groups, there's going to be an awful lot more chloride than sodium, and so chloride's going to be the dominant ion in that case, or the anions are going to be dominant, and then the ionic conductivity is dominated by the anions. So the bottom line is that concentration-driven permeability is dominated by the transport properties of the rare species, that is the co-ion species, and in ionic conductivity, it is the concentration diffusion coefficient of the majority species of mobile ions in the material that determines the ionic conductivity. In any event, within the framework that we're developing, we expect that if we had accurate values of the cation and anion concentrations in the membrane as well as their diffusion coefficients, that we could predict, for example, ionic conductivity from permeability measurements or vice versa. And so now I want to talk just a little bit about ion diffusion in charged polymers. This is going to be an entry into the last portion of this lecture. We've already talked about ion solubility and the basics of how the ion solubility fits into both permeability and conductivity. And now the last step is going to be to connect that up with models for ion diffusion in charged polymers, and then to go ahead and combine this to have a final expression for permeability and conductivity. So we bring together the expressions for ion diffusion, salt diffusion coefficients from the concentration gradient driven experiment that's shown on the right hand side of this slide, and the ionic conductivity expression shown on the left hand side of the slide. And these are experimental values. We can measure kappa by measuring permeability and salt solubility. We can measure the salt diffusion coefficient. We can also measure the concentration of cations and anions in the membrane, or calculate them using the Manning-Donnan model. And so what we have here are two equations and two unknowns. So if we know the cation and anion concentrations in the membrane, we know the salt diffusion coefficient, and we know the conductivity, the only two unknowns are the diffusion coefficients of the cation and anion in the membrane. We can solve those simultaneously to get individual values of these ion diffusion coefficients, and those are the results that I'll show you next. And I believe the paper that's given at the bottom of this page represents the first time in this field that this approach has been used to take integral measures of salt transport and back out single ion diffusion coefficients from them. In any event, this is the data for the resulting from that calculation for the anion exchange membrane, and what it shows is that the sodium and chloride ion diffusion coefficients don't change very much with upstream sodium chloride concentration, and the chloride is moving generally faster than the sodium. This is perhaps, at least at first glance, not surprising that if you were to look at sodium and chloride diffusion coefficients just in aqueous solution, the chloride is about 1.5 times as mobile as sodium. It has a smaller sphere of hydration of water around it relative to sodium, and so it makes a more compact structure in water that diffuses a bit more rapidly than hydrated sodium. Now, on the other hand, if we also look at the cation exchange membrane, we see that, again, there's not a lot of change in these diffusion coefficients with concentration, but now we see the opposite. We see that sodium actually appears to be moving faster than chloride in terms of its diffusion coefficient. And this would be a trend that would be opposite to the order of ion diffusion coefficients of these species in aqueous solution. And so that's somewhat counterintuitive. However, what we notice in both cases, both for the anion and the cation exchange membranes, is it is the counterion that is moving faster than the coion. And this provides clues that perhaps there are additional pathways for transport of counterions through these charged membranes than there are for coions. Now, I haven't shown you data for it, but if you did these same experiments with uncharged membranes, you'd find that always the order of the ion diffusion coefficients would be in the same order that you find them in solution. You wouldn't see this kind of differentiation where the counterions are moving faster than the coions. And so this prompts us to think back to the Manning picture, where the ions are partitioned into two different populations, one that is condensed and relegated to stay relatively close to the polymer backbone, and another where the ions that are farther away diffuse more or less like any other ions. There are a couple of factors that will influence ion diffusion coefficients in hydrated polymers. Now, we have talked about in the model of Yasuda, the free volume model, and how Yasuda correlated or identified that free volume in his hydrated polymer systems increased as the water content increased, and then correlated that his diffusion coefficients with water content via the free volume theory. There is a competing model, the so-called Mackey and Mears model, that actually in cases like these for charged materials has some advantages, and I want to explain what that is. It comes at the problem of ion transport through hydrated materials from a somewhat different point of view than the free volume model, but it gives qualitatively similar trends, and it requires fewer adjustable parameters. And so I'll show you how that works. We've also published papers showing the convergence of those two models, or the situations under which you get essentially the same values out of them. So Mackey and Mears imagined that in highly charged membranes, the ions were basically swimming through the water dissolved in the membranes, and that the polymer chain segments were acting as essentially obstacles that the ions had to diffuse around. Now, this picture is quite different from the one that we developed for ion diffusion or penetrant diffusion in polymers, for example, for gas separation applications, where the penetrants were relegated to staying in a free volume cage that was defined by the neighboring polymer segments, and the only way they got to move is when there was sufficient molecular motion in the polymer segmental backbone to open a gap large enough for the gas or small molecules to take a diffusion step. The situation here is quite different. These membranes are highly hydrated. They have, in some cases, a lot more water in them than polymer. And in this case, the polymer chain segmental dynamics are not the gatekeeping the ion transport. The ions are diffusing through the water that is distributed at large concentrations in this polymer, and the ions simply are required to diffuse around the polymer chain segments. And Mackey and Mears proposed a simple statistical treatment, a lattice-based treatment of that scenario, where the ions would diffuse essentially through a forest of polymer chains diffusing in and around the trees. And they came up with a remarkably simple model that's shown here, and it is that the diffusion coefficient of a solute or an ion in a polymer relative to the diffusion coefficient of that solute in a solvent is just given by this expression, where phi p is the volume fraction of polymer. Now, in these systems, there's often very little salt on a volumetric basis, even at high concentrations, and so 1 minus Vp is the volume fraction of water in the material. So again, like the free volume model, you see a model linking diffusion coefficients of solutes with the water content in the membrane. Now, these diffusion coefficients of, say, ions in water, you can go to a handbook to simply look those up, and so those values are tabulated. That's not an adjustable parameter. The volume fraction of water or equivalently the volume fraction of polymer can be measured by measuring the water uptake and the volume of the sample. So everything about this equation is determined, and it gives a model, a simple model, no adjustable parameters to calculate ion diffusion coefficients in polymers. And this is showing some data from the literature compared to this Mackey and Mears model. And you can see that at low polymer volume fractions, that is at high water content, the model does a pretty good job not to have any adjustable parameters, and it extrapolates properly up to the ion diffusion coefficient in water when there's no polymer. You can see where it starts to fall off as you get to, for example, materials that have only about 20 volume percent water and less. This model starts to show greater and greater deviations. And you might imagine that the reason for this is that at low water content, there's going to be a fundamental change in mechanism, that eventually the water content is so low and the polymer chain segments are crowded around the ions to such an extent that in fact it becomes the polymer segmental motion that gates the transport of ions through the material. And so this simple lattice-based approach, which neglects that that coupling to the polymer chain motion, will simply not work once the water content gets to be extremely low. Now, regions down here that we might be interested in would be things like reverse osmosis membranes. So we are highly motivated to seek other types of models that don't exist today to describe diffusion through materials that don't have, diffusion of ions through materials that don't have a lot of water in them. But for the ion exchange materials that we're considering, you remember that they were up in a range where they absorbed almost as much water as they had polymer in them, and so we're in a range where this Mackey and Mears model does a good job, as does the free volume model. The advantage of the Mackey and Mears model is that there's simply no adjustable parameters in it, and so we'll show how that is going to work here in a minute. So the way we envision ion diffusion in charged membranes, we break it up into two pieces. One is we first look at the co-ions. So if each of these fixed charges represents a sulfonate group, and we're permeating or conducting sodium chloride through this material, then the chloride would be the co-ion. And we imagine the polymer cross-link network as shown here, and looking at just a very small segment of it in a highly idealized cartoon-like fashion. We have the fixed charges. These little halos surrounding them are seeking to represent the Bjerrum length, and the fact that that these halos are overlapping between successive ions is representing the case where the Xc parameter, the Manning parameter, is greater than 1. That is, the distance between fixed charges is less than the Bjerrum length, and that's the case that's of interest for most of the ion exchange materials that we're interested in. Certainly, all of the ones that we've mentioned so far. And so, if we imagine a chloride sitting in this network and undergoing just thermal diffusion in the water that is between these polymer chains, we imagine that it executes diffusion and it is going in a direction of, for example, decreasing concentration, or going in a direction that drives it towards the appropriate electrode. So there's a driving force that moves it from left to right. And in taking these diffusion steps through water, the ion is excluded from going through the polymer chain, and it is also trying to minimize electrostatic interaction with the sulfonate groups that would have opposite charge. But basically, it is just diffusing through this network, avoiding the charged groups, and having to diffuse around the polymer chains. And so there's two variables or two phenomena that are at play here. One is the increase for the ion to cross this membrane. What is the increase in path length due to the fact that that the polymer chains are there? And this is a so-called tortuosity effect, that the ion has to travel further to cross the membrane because it has to go around some obstacles, the polymer chains, along the way. And then there can also be an electrostatic exclusion effect, so the ion is trying to minimize its interactions with these sulfonate groups, and that acts to further slow down its diffusion coefficient. But it turns out by just a little bit. The big effect is this tortuosity effect. And so this co-ion diffusion can be modeled using these two ideas. And so for the geometric or tortuosity effect, we use the Mears model, just as I've shown it to you a couple slides ago. And this nomenclature means this is the diffusion coefficient of the co-ion in the membrane relative to the diffusion coefficient of the co-ion in solution. So this value can be looked up in a handbook. The first effect, which is by far the dominant effect, is given by the geometric or tortuosity argument from the Mears model. Now, it turned out that Jerry Manning, in addition to publishing a model of the thermodynamic properties of ions in the vicinity of charged polymers, he also published a model in conjunction with that thermodynamic theory, which gave predictions for the effect of fixed charges on a polymer backbone on the diffusion of ions in the vicinity of the fixed charges on polyelectrolyte chains. That is, the presence of those fixed charges on the polymer backbone disturbs the electric field that the ions experience as they move and diffuse through the region near the polyelectrolyte chain. And Manning developed an expression or a model for how this inhomogeneous electric field would act upon and slow down the diffusion of those ions. And this is the electrostatic effect that's shown here. Now, I'm not showing what A is. You'll find it in Manning's paper. It's just a long double summation, an algebraic formula. It depends only on one grouping of variables, that is the fixed charge concentration of ions in the membrane, that is known as cation exchange membrane. This would be the number of sulfonates per unit mole of water in the membrane. And it depends on the co-ion concentration in the membrane. This we will know or have measured, and it depends on the Manning parameter, and that we will know or have calculated. And so together with this model, this is showing the co-ion diffusion coefficients in the cation exchange membrane. That would be chloride in the cation exchange membrane, and also in the anion exchange membrane. That would be the sodium, and a comparison to this model, which again contains no adjustable parameters. If you measure the water uptake, you know the volume fraction of polymer. If we know the characteristics of our ion exchange membrane, we can get at all these variables, and the diffusion coefficient of these ions in aqueous solution you just look up out of a handbook. And I can tell you that we cannot measure these diffusion coefficients as well as the model can predict them. So this is essentially quantitative agreement with this very simple model. Now, for co-ion diffusion, remember the counter-ion diffusion, remember the counter-ions had a somewhat different story. The counter-ions are moving faster than co-ions, and they're moving faster in co-ions under circumstances where that was unusual. That is, in the sulfonate-based cation exchange membrane, we saw sodium ions moving faster than chloride, whereas in aqueous solution and in the anion exchange membranes, chloride always moves faster, always has higher diffusion coefficient than sodium. And this makes us wonder if there is an additional mechanism of transport of the counter-ions in these charged membranes, given the work that Manning has done to show the importance of counterion condensation on polyelectrolyte properties and how well that works in ion exchange membranes to predict sorption, it might not be surprising that the counterion condensation is giving an additional mechanism for ion transport in these materials. And so we come back to the picture that I showed you a moment ago for co-ion transport, where we have just a small section of this cross-linked polymer network and blown it up, showing the fixed charge groups. There are Bjerrum links that are overlapping, and now a co-ion that's diffusing along here, avoiding the electrostatic interactions and diffusing around the polymer chains. We imagine for the free counterions much the similar path. They're staying near their co-ion and staying away from the polymer chains and diffusing, following much the same pathway and mechanics as the co-ions do. And so for the free counterions or the uncondensed counterions, we're going to use exactly the same model that we use for the co-ions and that I just showed you a moment ago. However, there is a second population of counterions. There are these counterions that are, in Manning's terminology, condensed or bound to the backbone of the polymer chain. And the question is, can they move? And there's evidence in the literature, from the polyelectrolyte literature, that they can, and that they move primarily along the polymer backbone, rather than moving away from it, although there certainly is an equilibrium exchange between condensed and uncondensed counterions, but they're largely confined to move along this polymer backbone. And so that provides another mechanism, an additional mechanism for counterions to be transported through this membrane. And if this reminds you qualitatively to something called the dual mode model that we talked about earlier for gas solubility and transport in gases, note that the physics are quite different, but the basic idea is the same, that the counterions at least have two modes of transport, two modes of sorption, two modes of transport through these fixed charge materials, whereas the co-ions have only one. Now, in modeling the counterion diffusion, we have to know what fraction of the ions are condensed and what fraction are uncondensed. Manning provides that expression. It's shown here. The fraction of uncondensed counterions in the membrane depends on the number of co-ions, because you have one uncondensed counterion for each co-ions, plus the fixed charge concentration on the backbone divided by the Manning parameter. And this reflects the fact that some of the fixed charges are shielded as a result of us having so many ions clustered around those fixed charges or condensed around them. And so the total number of counterions in the membrane is given, as before, by the number of co-ions. You need one counterion to balance every co-ion, plus the fixed charge concentration in the membrane. You need one counterion to balance each of those fixed charges. And then the fraction of condensed counterions is just 1 minus the fraction of uncondensed counterions. If the condensed and uncondensed counterions have different diffusion coefficients, and just show here that those fraction of condensed and uncondensed counterions, we can calculate them because we know all these variables, are about 50-50. So about half the ions are condensed and about half of them are uncondensed in the membranes that I've shown you. Now, if the diffusion coefficients of the uncondensed and condensed counterions are different, then the overall diffusion coefficient of counterions or Geoghegon in the membrane is just going to be the diffusion coefficient of uncondensed counterions, the diffusion coefficient of condensed counterions, weighted by the fraction of the ions that are condensed or uncondensed. So we have a really simple expression for the diffusion coefficient of the counterions. Now, for the uncondensed counterions, we use exactly the same expression that we use for the co-ions. That is, there's a geometric effect, the tortuosity effect from Mackey and Mears, and an electrostatic effect from the Manning picture. This is just the diffusion coefficient of the uncondensed counterions in the membrane, and this is the diffusion coefficient of the counterions or Geoghegon in the solution. This value you look up in handbooks. Now for the condensed counterions, we know less about what their mobility should be in the vicinity of those fixed ions, and so we postulate an empirical model for that. This introduces the only adjustable parameter in this model, alpha, and it gives the diffusion coefficient of the condensed counterions in the membrane relative to their diffusion coefficient in free solution, which again you just look up in the handbook, and we set it equal arbitrarily to a term that's labeled 1/3 alpha. The 1/3 is in there to remind us that this diffusion along the polymer backbone might be viewed as essentially a one-dimensional diffusion along a line or along a curve, and then alpha is a parameter that is gauging how much the diffusion coefficient of the condensed counterion is slowed down relative to its value in solution. And so one thing we should mention is that the ion diffusion coefficients in the membrane are always slower than they are in solution. The tortuosity effect accounts for most of that, the electrostatic effect for a little, but the ions always move much slower through the membranes than they do through free solution. And so we expect this parameter alpha to be less than 1, and that would just reflect that the counterions, the condensed counterions moving along the membrane, were slowed down by the presence of by the fact that they were condensed onto the membrane. And so the final expression for the counterion diffusion through the membrane is just the sum of the expressions for the uncondensed counterion diffusion coefficients, the condensed counterion diffusion coefficient, and then the fraction of each one. And so here shows the counterion diffusion coefficient in a couple of those membranes. And again, this to fit these data, we have to use an adjustable parameter, and it's on the order of 0.4 to 0.7. As expected, this value is less than 1, recognizing the slowdown in the counterion diffusion coefficient relative to its value in solution. Now, I've said a couple times that the tortuosity effect slowed the ions travel through the membrane quite a bit, and the electrostatic effect slowed them some, but not very much. And I wanted you to have a feel for that. So these plots are a little bit hard to follow, so let me break them down for you a bit. So this is showing the diffusion coefficient of the counterions and of the coions, excuse me, in the membrane relative to the diffusion coefficient of the coions in solution. And what you find for two different salts in this particular ion exchange membrane. And what you find is that the electrostatic effects reduce the diffusion coefficient of the coion relative to its value in solution by somewhere from 10 to 15, 5 to 15%. However, the tortuosity effects are a full order of magnitude. So the diffusion coefficient of the ions in the membrane are at least a factor of 10 lower than they are in solution, and most of that reduction is this tortuosity effect of the ions having to weave their way through through in between the polymer chains that make up the polymer network. This is showing a similar plot now for two anion exchange membranes, and looking at the coion concentration in the membrane relative to its value in solution. Again, sodium chloride is the salt that's being used here. And again, the electrostatic effects that slow down the ion diffusion are much weaker than just the tortuosity effects. And now we're going to wrap this discussion up, and we come back to our data that I had shown you earlier: permeability coefficient of salt, sodium chloride permeability through cation and anion exchange membranes as a function of upstream salt concentration. Now the dashed lines that are shown here are purely predictive. You'll recall that we showed a bit ago that the salt permeability coefficient is governed by the transport of the rare species. And in these charged membranes, it's the coion that's the rare species. It's the coion that Danon exclusion is trying to exclude from the membrane. And so to a first approximation, we can write the salt permeability as the coion diffusion coefficient times essentially the coion partition coefficient in the membrane. Because if the coions partition into and transport through the membrane, you can bet that a counterion is going to come with them. That's because there's just a great abundance of counterions. Now, this ion sorption value we can predict using the Manning model, and for that we need only the water uptake of the membrane and the polymer chemistry to make an estimate of the distance between fixed charge groups, no other variables. For the diffusion coefficient, we need only the volume fraction of water in the membrane to use to calculate the volume fraction of polymers. So if we measure the water uptake and we know the polymer chemistry, we can actually predict salt permeability coefficients to rather good approximation everywhere except at the lowest concentrations, and this may reflect some breakdown in the Manning model at very low concentrations where neighboring polymer chains are not electrostatically screened from each other. For ionic conductivity on the same materials, the same Nernst-Planck framework with the same value of the transport coefficients can be used to model ionic permeability, ionic conductivity, so electrically driven transport. In this case, we do have one adjustable parameter, that alpha parameter that's entering the diffusion coefficient of the counterions. So there's one adjustable parameter that can be used to describe both salt permeability as well as ionic conductivity. This is the first time in the 30 years of my career that I've seen a case where one could actually predict permeability of a solute through a membrane with no adjustable parameters. Now, once we've set the Manning parameter, and the data I showed you before is for sodium chloride, and we had calculated a Manning parameter of 1.9. Well, that same Manning parameter value works for any other salt that you might want to use, and you can see the model predictions line up with the experimental data almost perfectly, and so this provides a gratifying validation of the approach. And so in conclusion, in this section of the notes, is this Mackey and Mears model has been used to account for tortuosity and on diffusion coefficients, and the Manning counterion condensation model was used to account for the effect of fixed charge on ion sorption and diffusion, and we can predict coion diffusion coefficients with very good accuracy for the counterion diffusion coefficients, because they have two modes. That is, the uncondensed counterions transport much like the coion diffusion coefficients do, and the condensed counterions have an additional mechanism for transport through the membranes that requires an adjustable parameter. At this point, we can describe those counterion diffusion coefficients with just that one parameter, and that allows us to actually predict salt permeability coefficients, and using the same parameter values be able to describe ionic conductivity. Now, there are open research questions around this approach that are not resolved. The Manning model treats all ions as just point fixed charges. There's no chemical information whatsoever, so it cannot distinguish between, for example, sodium and potassium and lithium. It can distinguish between ions of different valence like sodium and calcium, but there's no further chemical information in there. And so being able to extend this to describe ion-specific characteristics would be of great help. We mentioned that the water content of these polymers is often a key variable to use with them. If we could actually predict water uptake, we could almost predict both water and ion transport with no adjustable parameters, and so that's something to really look forward to. I've shown you data today for only for single salts, and it's an open question about how to extend this to ion mixtures, which would be important in practical situations. We are awaiting whether molecular level modeling will confirm either the validity or highlight limitations of this approach. With these kind of tools in place, one might even think about designing materials with specified or tailored ion and water transport properties. What I've shown you here with the Manning model is for highly charged polymers. It only works in situations where the electrostatic interactions between fixed charges on the polymer backbone and ions are completely dominating the transport and thermodynamics. In other materials, for example, if there were no fixed charges and these were uncharged materials, the Manning model simply wouldn't describe the ion activity coefficients at all. For example, in uncharged polymers, those ion activity coefficients are not way less than 1 like we saw earlier in our discussion of ion activity coefficients in these charged materials, but ion activity coefficients in uncharged materials are actually much larger than 1. The ions don't want to be in those materials. The Manning model can't predict that, and so we need other models, perhaps related more towards a Florey type approach, to be able to estimate ion activity coefficients in those scenarios. And then we need tools to bridge the predictions from uncharged all the way to highly charged materials. And finally, could this framework apply to ion transport in non-aqueous mixtures? If you look at scenarios where ion transport through electrolytes and through polymers is important, there are other applications like battery applications where the electrolyte is not water, and so if one could model transport in those scenarios, then that would be truly a great accomplishment and a great extension of this. And with that, I will end this lecture. And thank you for listening, and thank you for your time.